Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Collect and store this and get the static representation that we need, that we actually annotate the dynamic information on. The applications we are looking at is dynamic slicing. So let's say you run a program and somewhere it crashes, which is this red dot. The slicing tells you, finds the set of statements which are likely to contain the faulty code. And so there are different types of slices. You can do it on data dependencies and control flow and data dependencies, and the third kind of slice called relevant slice. And they are increasing in their size, but they also are increasing in their effectiveness of capturing faulty code. So just to give you an idea, so for example here when we see this one line across, we see that the number keeps increasing because the number is increasing, and what that means is that more often the faulty code is in the slice than not. And in case of data slices, many times it's not there in full slice, it's most of the times there in relevant slice, all the time it's there for certain kind of errors which are in assignments or predicates. Then so of course relevant slice is a good thing to use, but the size of the relevant slice is bigger than the full and the data slice, so that's the payoff. But nevertheless, the size of the relevant slice is still significantly smaller than the program size, so that's why it's useful. For matching, I mean, so here the idea is if you have two versions of the program and you want to compare their behavior to see what part matches and what part is different, so that's what essentially matching does. Now, one instance where you want to match things is when you have optimized and unoptimized code. And maybe you made a mistake in the optimization, in the implementation of optimization, so the programs don't behave the same, although you expect them to behave the same. So you can compare the executions of these two programs and see the differences to see where they actually, things went wrong. But to compare them, you need a mapping between the unoptimized and optimized and unoptimized code so that you know what should match what. Without these mappings, you don't know what to compare with what. So, but the problem is that getting these mappings is a lot of work, because you have to actually, as the program is being transformed, you have to track these mappings. So instead what we use is we just use traces, where what we do is we actually look at the trace and we match the traces of the two programs. If they match, then there's a good chance that they're doing the same thing. If they don't match, then that's the part where something may have gone wrong. So if you match the optimized and unoptimized program, for 95% of the optimized statements, we were able to find a match. For few, we couldn't, and that's this bottom line that's showing that small number of statements we couldn't find a match. But if there's an error, suddenly this number increases quite a lot. So that's how you could use this. You do this matching, and when the matching starts to give very big differences, that's where program has stopped functioning, essentially. So instead of using mappings to match, we are doing the matches to find the mapping in some sense. So now let me go back to the tracing part, because that's where we're actually using Phoenix. And this is a piece of work we just finished where we made use of Phoenix. And here the idea was that, as I told you before, we want to collect these traces, store them in compressed form. So we want to capture control flow traces, we want to capture data dependence traces. So you can capture them separately, store them separately. So here we explored an intriguing idea, which is that is it possible to implicitly represent all the data dependencies in the control flow trace? So you only have the control flow trace, and from there you can recover the data dependencies. So what we had to do to essentially show that this technique is effective is collect control flow traces, collect dependence traces, and then collect the new kind of control flow trace, the extended trace, where the data dependencies are implicit in it. So we used this, and it was fairly straightforward to use Phoenix for this work. And I mean, in terms of programming, it was very minimal programming we had to do to collect these traces, and essentially be able to generate the instrumented binaries through which we got all this information. Now what we are further doing with this is that this is just part of the traces, but the whole thing that I talked to you about in the beginning, the whole whole execution trace representation, it requires a static representation of the program which has been transformed in a way that the dynamic information can be effectively compressed. So that's the next step we are working on, to make use of Phoenix to generate this transformed static representation. So far our transformations have actually been just instrumentations. There we will actually have to go ahead and change the code and so forth. And actually that's where we are. So that's all I have to say.
Chandra Klintz from University of California, Santa Barbara.
Thanks. Okay, okay, so what we're interested in doing is something a little bit different than the last couple talks. What we're trying to do is develop techniques that allow us to do profiling online while the program is running. And so what we have to get, or what we have to achieve, is very, very lightweight, a very, very small overhead when we do our profiling. So the way we're going to do this is via sampling. By sampling the execution, we're able to get a picture of the executing code. At the same time, we want the resulting profile to be accurate. We want it to look almost exactly like as if we had exhaustively profiled the entire program. And so that's the overall goal. And what we're interested in is, once software has been deployed, to be able to monitor and extract information about that code in order to do some software engineering and software evolution remotely. Either we could do it remotely at the development site or on the device itself. And so that's where we're headed. In order to achieve this, though, we need to have a really efficient, lightweight sampling mechanism. And that's what we're doing with Phoenix. We're actually implementing in Phoenix tools that hopefully will be used by the community that do two things. The first thing we need is to be able to turn on and off profiling dynamically. We don't want to have code instrumented code executing all the time. We only want it to be executed when we want to take a sample. Once we have that capability, then we have to have intelligent mechanisms to decide when to turn profiling on and off. Okay, so there's lots of ways to do sampling. You could simply just take the execution trace and just periodically, after fixed periods of time, take a sample. You could do this randomly to get better code coverage. But what we were interested in is, because we're interested in optimizing or improving the performance of code, we want to sample according to program behavior. And there's a lot of work in this area that shows that doing so is very effective for dynamic performance improvement. So what we are going to do with Phoenix, or what we're working on with Phoenix, is we're enabling the capability to turn on and off profiling dynamically. And what we're going to do, or what we've implemented, is the same technique as Arnold proposed in 2001. The idea here is you're going to have a duplicate copy of your code. One has no instrumentation in it, and the other one is instrumented. And the idea, and then what we'll do is we'll transfer control between the two when we want to take a sample. So when we're not sampling, we'll execute straight line code, it'll be very, very fast, and then every so often we'll jump to the instrumented version. In order to know when we want to jump, we can just use simple counters. And again, we want to be able to keep track of where time is being spent in the program, so we can use things like threshold-based counters at the method invocation, as well as on loop back edges. As Brad mentioned, it's really important to capture loop behavior, because you might not execute a method very often, but you might spend a lot of time in there. So once you reach some threshold, what you'll do is you'll transfer control to the instrumented version of the code, and you'll take your sample. This sample, again, is instrumented. It has extra code in it, extra instructions in it to collect the data you're interested in. And notice you can instrument this copy in any way you want. Now, what Arnold proposed was that you jump into this code, you'd execute this code in a single pass, and then when you hit a method call or a loop back edge, you jump back to uninstrumented code. So you wouldn't spend very much time in instrumentation, so it'd be very fast. Another alternative is you might be interested in a profile that's has temporal relationships in it. For example, you might be interested in the memory accesses that your program makes, and the order in which those happen are important to your profiling. So Trishul Chilimbi here at Microsoft Research extended this idea in order to add additional counters in the instrumented version so that you could stay there longer. What we've done with Phoenix then is to give you the capability of manipulating this, it's called bursty sampling mechanism. You can easily now jump between instrumented and uninstrumented versions to turn on and off profiling dynamically. And you're in control. You can actually do a lot of experiments with this. You can manipulate any of these threshold values to see how often you want to sample and how long you want to stay in the instrumented code. Another thing you can do is specify any type of profile you want. Anything that Phoenix can do, we can do in terms of the instrumentation. So it's very flexible to that extent. Okay, so now you have the capability of turning on and off sampling dynamically. You want to be able to now decide when to turn it on. We want to do this very intelligently. Again, our goal is very low overhead. We don't want to sample very much, but yet we want accuracy. We want the profile we create to be almost exactly the same as the exhaustive profile. So what we're doing is exploiting the repeating patterns that Brad talked about earlier in program behavior called phases. And again, what's happening here is these are just timelines of a computer program and a bunch of hardware metrics. And all I want you to take away from this is that there are repeating patterns that we can exploit. So if we wanted to sample this program, let's say, we could do periodic sampling, like I mentioned. And periodic sampling, the problem with this is that you are collecting lots of redundant information. You're going to sample periodically, which means you may be sampling the exact same thing over and over and not getting any new information. You also might miss big chunks of code that are important to your performance. You can do random sampling. You get more statistical guarantees about the coverage you're getting. But again, you could be hitting sections of the code that you've already sampled, or you could be missing things. Bursty sampling can be used to do your sampling like we talked about earlier. Commonly, if you just use the straight bursty sampling, you're going to find hot portions of your code and you're going to stay there. So it's unclear whether you're going to be able to cover all your other code. What you could do is change the counter mechanism in order to get a better coverage, but there's a lot of counters that you'd have to manipulate. So our idea is just to use phase sampling, to sample according to phases. If a phase executes and you're able to take a sample of it, you have a picture of what the entire phase is doing. As long as you can keep track of how often that phase occurs, you have a very accurate picture of the program's execution. What we found, so then if you're using phase sampling, then whenever a new phase occurs, you take a sample, you turn on profiling. And so in this case, when a program that only has 4 phases, you'd only need to take 4 samples to get a very, very accurate picture of the program's execution. What we found is that with 5% error, that is, the sampling profile is 95% the same as the exhaustive profile. We're able to reduce the overhead by 55 to 80%. For the programs that we looked at. So our conclusions are that Phoenix provides you with a really nice framework to investigate interesting techniques for profiling and for performance optimization. And what we've done is extend this framework to give you the capability to turn sampling on and off dynamically by doing copying the instrumented version of the code. And then we've given you an intelligent technique that tells you when you should turn on sampling in order to get very high accuracy with very low overhead. Now, this technique requires that you know when phases occur. So what we've done is we've connected Phoenix with the hardware performance monitor interface of Windows, and we're able to look at correlations across hardware performance counters to determine when a new phase is occurring. Alternately, we could just as easily use Brad's technique for phase marking. And then lastly, which I don't have time to talk about, is I have a really nice visualization tool that once you can produce these phase profiles, you can visualize them. And this really helps in identifying performance bottlenecks and also in developing optimizations. You can really focus in on, filter all this performance data to find, to guide how to do effective techniques in optimization. So with that, I'm finishing. I just want to say thanks to the Phoenix team as well as to my excellent students. Thank you.
And Professor Vladimir Safanov from State University, St. Petersburg, right?
We are using Phoenix to develop our own aspect-oriented programming tool, referred to as aspect.net. So actually, our aspect.net project was 3 times granted by Microsoft Research, and actually conceptual work on this project started in 2002. The goal of this project is to develop a state-of-the-art aspect-oriented programming tool, which will be integrated not only to Phoenix, but also to the latest version of Visual Studio.NET 2005, Whitby. Informally speaking, our goal is to make AOP, or aspect-oriented programming, really a ubiquitous tool and technology, as well as Visual Studio.NET, so that each software developer could use our tool together or integrated to Visual Studio.NET. And of course, our purpose was also to develop a most adequate way of representing aspects for Microsoft.NET and lay the foundation for future research and development work in this area. A few words about aspect-oriented programming itself. So actually, AOP is a prospective software development paradigm and technology, which is based on the concept of a cross-cutting concern and aspect. Actually, the predecessor of aspect-oriented programming, which is probably not well known in the US, is Professor Adolf Fuchsman from one of the Russian universities, from Rostov University. Actually, the ideas of AOP, or similar ideas, originated very long ago. It is quite natural, because AOP is a kind of activity which each software developer sometimes performs implicitly or intuitively each day or each week or each hour of his or her work. And so our goal is to make a tool to have the AOP be applied in more comfortable way. And of course, it is well known that now the modern classicist of AOP is Professor Gregor Kichelis from University of British Columbia, who originated his famous Aspect-J project in Xerox PARC company. But his tool is based on the idea of aspect-oriented extension of Java language, which somewhat limits the flexibility and applicability of this tool. A few words about concepts. So cross-cutting concern is a kind of concern or idea or consideration which can be applied or found in a program or added to a program, but which cannot be implemented just by one model, by class hierarchy, and requires insertion or replacement of tangled fragments of code which are concentrated or located in different parts, in different modules of any application. Typical examples of aspects are logging, security, empty safety, and my favorite example is, so let's take a compiler and add some new construct to the source language. For example, let's take C# without generics and let's add generics to it. And everything which is needed to be added to the compiler, in this case, can be considered as an aspect. Aspect actually is an implementation of a cross-cutting concern, which consists of course, some related modules, but also consists of some tangled pieces of code. It may be declarations, definitions, statements, in particular calls of methods or functions, which are to be inserted into a target application to extend its functionality. So the process of inserting or adding an aspect is referred to as weaving. So weaving is inserting an aspect to a target application or target module. So another concept is point cut. Point cut is a set of weaving rules for an aspect. And join points, another fundamental concept of AOP, is a set of concrete points inside the target application, subject to applying or weaving some aspect. So actually join points are the points in the target application where to add fragments of some aspect. Of course, benefits of AOP is to make software development and maintenance easier. Our approach to AOP is quite different from approach of Gregor Kicalish and many other researchers and development companies. Because, so due to the fact that we are developing this tool for Microsoft.NET, of course, we decided to make aspects for .NET really language agnostic, and that's why we are weaving aspects at the level of .NET assemblies. But of course, we needed a good tool for that. And before Phoenix appeared, we had to invent something by ourselves, like any other researchers do from many countries, in particular related to Router academic program. Our project is actually part of Router academic program. So, to simplify, to make easier definition and application of aspects, I developed a very, very simple aspect definition meta language. Actually, this language is applied as a set of annotations, or AOP annotations, which just can be considered as a comments. But actually, we use Phoenix to handle assemblies and to support weaving, because our weaver, which is part of our Aspect.NET tool, generates or uses Phoenix IR, which is much more comfortable for weaving than using directly .NET assemblies whose structure, whose architecture is quite complicated. Another goal we achieved was to develop Aspect.NET as a Whitby add-in. So Visual Studio.NET 2003 and 2005, as well known, provides mechanism of add-ins. So due to that, at each start of Visual Studio 2005 in particular, your tool appears, or related GUI appears actually as part of this call of Whitby. The architecture of Aspect.NET is as follows. Since we provide a simple meta language for aspect definition or a set of aspect-oriented annotations, we have to use a specific converter or converter for each .NET language to convert this annotated source into the ordinary source in C# on the Visual Basic.NET and so on. Then Aspect Weaver takes target assembly and so assembly which represents aspect and generates, applies or weaves this aspect and generates the updated assembly. What is very important is we represent aspects by custom attributes, which is quite comfortable, as opposed to many other approaches, because some developers or some researchers represent aspects by interceptors, some others represent them by XML files, which are separated from the code. But our idea is to have aspect representation integrated, safely integrated to the assembly code. Then another part of Aspect.NET architecture is Aspect Editor and Aspect GUI, which allows to load aspects, to choose join points, which is very important because it is much more comfortable for a user if he or she has an opportunity to choose to which join points to apply aspects or to which join points not to apply aspects. Because blind application of aspects can lead to, unfortunately, can lead to a program which is maybe not recognizable or not debuggable. Then we also have part of our system which performs aspect coloring. So each aspect can be colored and located more easily due to that. This is a simple example, probably the simplest aspect is politeness. So let's make target application polite by adding hello at the start of the call of each method and by the end of the call of each method. So in bold AOP annotations are represented. And you can see that the rest part of the source code is just ordinary source in C#. And this is a construct in our meta language which provides, or which defines how to apply an aspect to some application. Of course, the same can be done by special GUI. This is one of the screenshots of our aspect.NET tool. So you can see that aspect.NET framework is actually part of VB GUI, and it represents the aspects and set of join points which are found by the viewer, and you can select or unselect any of them. Then in the output console you can see a trace back of working of our system. And this is an example of aspect coloring. And clicking to each of these lines, you can visualize in the source code the appropriate join point, which is quite comfortable. What is the current status of aspect.NET? Now we have a working version, working prototype of our system, using the latest Phoenix RDK and using the latest Visual Studio.NET 2005 Beta 2, or VB Beta 2. I have a good team of developers of aspect.NET, of implementers. And by September 2005, by Router Workshop, which will be held also here, we plan to have a complete working version of aspect.NET, which means that we'll complete development of the version of our system which will be working in the Router environment. In perspective, we'll develop a useful library of examples of aspects which can be applied to any module or application. And also, we have started research on aspect mining or aspectizing, which means locating aspects in non-aspect-oriented programs. I am ready to demo from my laptop, but for some reason, sorry, I cannot display it on the big screen. So to any who wishes, I can show how it works on some interesting examples. By the way, one of the examples is as follows. We have taken one of the examples which is provided with Phoenix RDK, I mean managed add knob, and instrumented it some way using a special aspect. So we calculate the number of knobs which are added by special aspect and so on. So much about the demo. And here are some references. In particular, number 4 is our latest article, which is to be appeared or probably already published in the latest issue of .NET Developers Journal. All in all, we have published 3 articles on our project in .NET Developers Journal. So thank you very much to Phoenix developers and for such a great tool.
Sure. And now Mike Smith from Harvard is going to tell us some of his experiences.
Thank you, John. So I'm going to stand up here as an advocate for Phoenix. As John says, a number of us have been working on this for a while. And there's really 2 reasons behind my enthusiasm for Phoenix. First is just the fact that compilation is creeping into everything. I've listed a couple of things up here: virtual execution environments, security systems, instrumentation systems, as you've heard from some of the other speakers today. And those are just the kinds of things that I'm interested in. Phoenix is meant to support a lot of other kinds of tools and infrastructures too. Second of all, I look at Phoenix as a substrate for the kinds of research that I want to do. It will help me unify the efforts that I have going on in these different areas, so I don't have students running around in 13 different infrastructures and I can't keep track of what they're keeping up with. And for those of you that know my background, I've done a lot of infrastructure building. We'll talk a little bit about it today. And I'm very happy to get out of that game where I don't have to spend time doing the infrastructure. I can actually focus on the research. And I want to try and talk a little bit about how I'm going to make that happen today. So in my 10 minutes up here, which will hopefully be 10 minutes, I'm going to try to answer two questions here. First of all, talk a little bit about the research that we have and how we're moving the kinds of things that I'm interested in today onto the Phoenix platform. I'll talk about some work in static compilation and a couple of projects we have ongoing in dynamic optimization. And I've also got some work on security and privacy that we hope to migrate over to Phoenix in the future too. Unfortunately, I won't be able to talk about that today. And then second of all, in the second half of the talk, what I want to do is focus on why I'm actually going to hide Phoenix as the underlying substrate so that the students that I have working on this project don't even have to really understand that they're working on top of Phoenix. And there's really three reasons for that, as we'll see as we go through the talk. The first is I want to use this in teaching. It's one of the greatest ways of getting students involved in our research projects. And as we'll talk about a little bit later, it's going to be difficult with the size and the scope of the project that Phoenix is today. I'm very interested in minimizing impacts and changes that Phoenix has as Phoenix evolves itself. I don't want to have that affect the kinds of projects that my students are working on. We'll talk about how we can have that occur. And then finally, I really want the extensions, because Phoenix is built as a system that's supposed to be extensible. I want those extensions to really be indistinguishable from that which is directly supported by Microsoft in the system, and we'll talk about why that's an important goal too. So let me talk a little bit about our research. I was actually here last year and I talked a little bit about this project. It was some early results. We have finished work and porting over a register allocation algorithm that we actually presented at PLDI last year. It was a graph culling register allocator. It basically made Chaitin's very popular approach work for modern machines today. And for those of you who know Chaitin's approach, it works well as long as you have very regular architecture. As soon as you have a couple of warts in your architecture, which all architectures do, it was very difficult to apply and people would have hacks in the world. So we went through and have actually implemented that within Phoenix. We used a bunch of their extensibility features. We ended up writing a plugin that allows us to replace the current register allocator inside of Phoenix with our register allocator, and we can do some experiments there. We actually didn't push very hard on the systems. A lot of the work that I like to do tries to change things within the compiler. So we didn't actually change any of the underlying IR in the system, but we did extend some of their classes and so forth. Some of the work that we're trying to do now I think is going to push much harder on Phoenix, and that's why I'm talking to these guys a lot. So what I want to do is just briefly talk about two efforts that we have ongoing in dynamic observation and dynamic optimization, and the driving observation behind both of these pieces of work is the fact that runtime optimization really differs from compile time optimization. I love doing optimization. We've done it for a long time in the compiler, and now I want to be doing it in these runtime systems. And when you're in those runtime systems, these optimization efforts, obvious point, optimization efforts have to pay off. But they really have to pay off. It's not like I was doing in the compiler where, yeah, I can stick another phase in there. If it happens to produce some better code, wow, good. If it didn't, no big loss because I was doing it compile time. You can't get away with that in the dynamic optimization system. And we'll talk about some of the things that we're trying to do today in terms of combining optimization, some phase ordering work, and so forth that should help us understand better what optimization efforts will pay off. Second idea is contextual information. If you look inside of dynamic optimization systems, I'll briefly talk about in a moment, things like traces are pulled out of the execution stream and we're supposed to go and optimize those traces. It's supposed to look like superblock scheduling and when who is done for a long time. It doesn't really. If you look at it, you don't have the contextual information about what other traces are connecting into the superblock to play with it and so forth. And that's going to cause us to want to do some things that we've been doing in region selection, which I'll briefly mention today. So let me start with the combining optimization works. We're actually taking a much larger view of the system here. Kelly Heffner, a student who's actually at Microsoft, she's up here in the front row, is working on this work, and a student of Norman Ramsey's, Kevin Redwine, are doing this work. So we're basically trying to put together a tool for exploring the optimization space. This is very different from the kinds of things that you may have heard Keith Cooper or Mary Lou Sophos in the back talking about. What we're trying to do is use a rules engine and representing optimizations as inference rules to really go through and quickly look at different kinds of optimizations, combine different types of optimizations together to see if we can come up with something that's going to give us a lot of bang for our buck. And as you might imagine, trying to do this very different from our normal kind of compiler, there's a lot of challenges in this, and they're not just within the optimization framework. And be happy to talk to you about some of those things afterwards if you're interested. In terms of the region selection, this work was done by Dave Hineker, who's actually an undergraduate at Harvard, who's now at Microsoft. You might catch a pattern here. And Kim Hazelwood, who is now a faculty member at the University of Virginia. So I'll give you a little background here for those of you who don't know a lot about dynamic optimization systems. In these systems, you have to be very careful about the kinds of regions that you select. These regions are going to limit the types of profiling and optimization overheads that you have. Every piece of code that you pick up and go put in your code cache has to be optimized, has to be profiled at some point. And getting good region together allows you to pull these frequently executing pieces of code together, and that will allow you to do better optimization. So what I'm really interested in is trying to get together and put the regions together that make a lot of sense for optimization. If you look at the systems today, you basically have two choices for region selection. The JIT-like systems, those things behind Java and so forth, are just taking whole methods and compiling them, doing some inlining and so forth. Most of the other systems that are really talked about as dynamic optimization systems are using traces. And that's what we're going to focus on, or my work right now is focusing on trying to improve on traces. And if you look at the systems that do trace-based dynamic optimization, a lot of them are based on the original Dynamo work out of HP and their technique called next executing tail. And what we're trying to do is really do better than this technique. And so just to give you a high-level picture of what we're trying to do, we're trying to say what are the things that are not working well in net today. There's basically two issues that you deal with, which we talk about as a problem of separation and a problem of code duplication. There's more code duplication going on in this technique, and there's more separation. You get good locality within the traces, but you're getting lousy locality within the code cache between these traces. So we'd like to come up with techniques like the first one up here, last executed iteration, which is actually allowing us to group together the code that executes around a loop body. And obviously we can optimize better than splitting that code into two different pieces of the code cache. Get some duplication out of the world too. And then dealing with the non-highly biased branches, right? We want to make sure that we can do something about that. And I don't have time to go into all these details. We're in the point now where we're trying to figure out, are these types of region selection algorithms, we've shown that they're better for separation and duplication, but are they actually better for us in terms of optimization? So to switch gears here for a second and answer my second question, I want to talk about something we call OPI Phoenix. And this is a port and an update of something we called OPI SWEEF, which was OPI standing for Optimization Programming Interface. It was this interface we built when we were working on our original compiler project called Machine SWEEF. The infrastructure there was on top of SWEEF. So the whole idea behind the Optimization Programming Interface is, first of all, to isolate the optimization passes from the underlying substrate, so things like can change in the underlying substrate and not affect your code. From the point of view of using this in a class, I want the code that you look at to look very much like textbook code, so that it's easy for students to write, easy for students to understand. And it also puts the core system features and later extensions on an equal footing. So as you'll see in a second when I show you some code, you can't tell whether somebody added this to the system or it was original fact within the system to begin with. Makes it much easier to deal with the system moving forward. So the result is you get a system that's better for teaching, and in my opinion, it's therefore better for research too, because I want my older students producing stuff that my newer students will work on, and things being produced by Mary Lou's group being able to be used directly in my group and not have to worry about what was in the system to begin with. So just a little history here to understand the context. So OPI SWEEF grew out of this concurrent development of SWEEF and Machine SWEEF being my project. SWEEF was the substrate for Machine SWEEF. We're building on top of that. And here are the headaches we had. Well, we hated it whenever they would inevitably change some aspect of SWEEF. We were doing concurrent development. And we didn't own the source to SWEEF. And we, of course, wanted different capabilities in it because we were doing different research than they were doing. But since we didn't know the system, we couldn't easily put that into it. Now, I don't want to pick on the people that defined SWEEF because we had the same problem. We were trying to produce something that our users were going to use. So Machine SWEEF was a substrate for XSWEEF, whatever you wanted. And our users hated it when we changed something in Machine Sweep, and they didn't own the source, we did, and they had capabilities they wanted in the system. So this recursive problem, we had to address this problem and make it easier for people to add to the system and to share the system. And hopefully you can see that this actually corresponds to what's happening in Phoenix. The research community will use, I certainly don't want to own Phoenix. I'm getting out of the infrastructure business. And if you listen to some of the talks that the Phoenix people give now, the API is still evolving. I don't want those changes to directly affect the work that my students going on. I want them to be insulated from it. I'll pick on Andy if he's here. He may not be here. There's Andy. So I was listening to one of Andy's talks recently. He gave a wonderful talk on the Phoenix IR symbols and types, and I take one little quote out of his talk. So he talked for 135 minutes and said, oh, by the way, this is just a superficial overview of the IR types and symbols inside the system. And I look at that and I go, that's not going to happen in my class. So Phoenix has been built to be extensible. You can do a lot of nice extensible things, but there's really no guidelines on how to build compatible extensions. And that's one of the things we're trying to address here. So here is a piece of code for doing spilling of source registers from our original OPI Sweep world. And what I've done is colored the types and functions that were in red and blue for the things that came out of OPI Sweep. And it's supposed to be very readable for you. And if any of you are Machine Sweep users, you should know that we're trying to maintain as much of that moving forward as possible. So here it is under OPI Phoenix. We've made a couple of cosmetic changes. We're now using, as we'll talk about in a second, C# instead of C++, so we lose all our stars. And we've gone to camel case, which is an easy copy replace kind of change so that we're more up to date. But otherwise, it should be as easily readable and so forth. So just to summarize the kinds of updates we're looking at for OPI Phoenix, we're using C# now instead of C++. And what this really means is we're actually, even though it wasn't apparent from the last slide, we're using real object-oriented style now instead of the C style that we were limited to under the original C++ compilers we were using. And we're making some stylistic changes like better iterators and so forth. The other thing that's happening in terms of OPI Phoenix versus OPI Sweep is we were developing a low-level IR at the same time we were doing the OPI, and we've learned some of the IR stuff crept in. Phoenix gives us a low-level IR. I don't need to develop it. So we're just eliminating those things from the world. So in conclusion, which I'm probably over my 10 minutes, we're looking to use Phoenix in many different research projects. The common thread is the need to generate, analyze, and optimize code. And we're also looking to make Phoenix an outstanding platform for teaching and for research that builds on the work of others, so that we can all start sharing the things that we do as opposed to redoing them. That's all I have to say.
Thank you. I don't want your phone. I want the. Yeah. So we've seen several uses of Phoenix in research. And at least to me, it was kind of exciting to get some updates on what we've been doing. I'd like to give you a bit of an update on where Phoenix is for the academic program and how we can continue to make Phoenix available. We've made some progress. Right now, in order to get a copy of Phoenix, you have to sign a non-disclosure agreement with Microsoft. And that makes it okay to use in research, but it's pretty hard to use in an instructional environment. We've had a few classes that have been using Phoenix, and every student has to sign the NDA, and that gets a little painful. So I'm able to tell you that come fall, the current schedule is October, right, team? We will have a version of Phoenix that will not require an NDA. It will be a conventional EULA. Think of it as a shrink wrap and use a license agreement. For non-commercial use only, Phoenix will not be available for commercial use in this main way. But for non-commercial use, we will have Phoenix available. It will be a download off a website. And the idea here is to make it feasible to use Phoenix in instructional mode, as well as continue to make it available for research. There still will be reasons that it will be advantageous to have a non-disclosure relationship with Microsoft if you need deeper use of Phoenix. And if those come up, we will continue to have the NDA agreement so that we can have that stronger relationship. But for general classroom use, this availability in the fall, currently scheduled for October, looks like a real opportunity. Yes? I hope it's not October 45th. Let's put it that way. Okay. I'd like to leave it at October at this time. We'll be doing a few other things with this release, in that one of the big issues for making something so easily available is the support issue. And it's really not going to be feasible for the Phoenix team to support every student who has access to Phoenix and answer their questions. We're not a formal product, we're under development. And so, frankly, it ends up being the engineers on the team that have to answer the questions. And if they're answering questions, then they're not doing the job that Bob wants them to do, getting the code written. Yeah, you. So we will continue to make the website available for answering questions that we've had, hopefully improved, actually. But it will be open to the principal investigators, to faculty, to teaching assistants. We are not going to enable general student access. And I think it's for fairly reasonable reasons. Another thing that we're just getting finalized, in fact, I got a mail today that we're finalizing it. When you have access to this website where you can report problems and ask questions, you also will be able to directly report bugs right to the database that the Phoenix teams gets their bugs out of. That doesn't mean that those bugs are going to be all high priority, but it's an opportunity to report things into the team's bug database, make your suggestions, report your bugs, and that will help ensure the feedback actually gets to the team. The current distribution of Phoenix is over 100 meg, as I recall. We believe the download will be closer to 25 megabytes when we make the final distribution. And we're also working on a process to make it easier to do periodic updates to it. Right now, we've averaged something like 2 releases a year for a few years. We probably want to try and improve that, though there's some support questions along those lines. But in any case, we will have the ability to make quicker updates. What this RDK will contain is the current version of Phoenix as of as of the end of August or sometime in September. So we'll have a lot of new features. Things will have changed. Interfaces will have changed, just like Mike well knows. The current distribution of Phoenix is both a managed and an unmanaged version. In this non-NDA version, it will only be the managed version of Phoenix. Based on the feedback I've gotten so far, that's at the very least not a problem. So that helps make it a smaller download. It makes it more manageable, I guess. We've got a number of samples. We've added samples beyond the samples that are in the current RDK, so we're continuing to evolve the sample code that we've got. We've got a wizard that helps build, lets a student help build their Phoenix program, so you don't have to do all the cut and paste from scratch. We're building tools to make it easier and make it more approachable to start with Phoenix. It's integrated into Visual Studio. It's actually integrated, it's actually integrated into Visual Studio, not more integrated, but it's actually integrated into Visual Studio. It will depend on Would-Be Beta 2 when it comes out, because Would-Be Beta 2 will be the current release at that time. And those of you who are using Phoenix right now know we have a small problem in that we require Would-Be Beta 1, but Would-Be Beta 1 expired on July 1st. So we're going to get you the Would-Be Beta 2 version. The documentation that you've had before you will continue to have, and some video from a workshop that we did a few weeks ago will be available as part of this as well. So it'll be the written documentation as well as video talks and the sample code and so on. Certainly, Our goal is to make it easier to use. We want a fairly good user experience when people turn it on. That's been one of the major focuses from the team. The setup is a lot simpler. It's a lot smaller. It will go faster. We've done some I think some pretty amazing work in producing some walkthroughs where rather than just giving you a piece of sample code, we have documentation that tells you, okay, this is how you do it. You start up Visual Studio, you launch the wizard. We wanted to write this kind of program, so we chose to edit what the wizard did this way, and so on. So really nicely done walkthroughs. I believe the plan is that we'll have at least 3 or 4 walkthroughs when it ships. So I believe we have 1 complete right now. And of course, we're continuously updating the documentation. Now, Matt Mitchell is one of the interns who's been working on Phoenix, and he's been heavily involved in building this RDK. He'd like to show you a little bit of what we've been able to accomplish.
So one of the big things that we're pushing with the next RDK is reducing the entry cost of somebody just picking up the RDK. Installing on their computer should be simple. We're pushing Visual Studio integration, as John was saying. We want to have people be able to install this RDK, open up Visual Studio, generate some code, and immediately start working on Phoenix and not worrying about a boilerplate code. So one of the things we're working on is a set of wizards that do everything from generate sample backend phases, basically skeleton code, generating static analysis tools, just basic phases, and also Visual Studio integration with Phoenix. One of the things we want to do is have people write tools for Phoenix that run inside Visual Studio. So if, say for instance, I'm building a project, I want to have output from Phoenix that displays some kind of a static analysis. Now, when I have that happen, immediately I can hit build, Phoenix will run, produce some kind of an output and display it on the screen. So I've been working on the last couple of weeks on a control flow graph add-in that will allow you to right-click on a function in the class view and display a control flow graph from a built binary. And we based this off one of the wizards that we've written that generates the Visual Studio add-in. So we have a whole set of wizards, and they do all kinds of things. They set up basic drawing surfaces. They set up menu items, toolbar items, and so basically you have everything set up so that you can go in there, you can add a little bit of boilerplate code, or a little bit of code to interface with Visual Studio, and then start working on your Phoenix stuff immediately. So I have this sample project. I have this add-in already built, but basically what you can do is you can right-click on any function, grab the control flow graph, and view basically a simple linear format where it displays the Phoenix IR, arcs for the jumps, and basically it illustrates a couple concepts within Visual Studio of how do we interface with Visual Studio, how do we interface with Phoenix, and how do we put all that stuff together. And as John was saying, there's a walkthrough for this that will get distributed with the RDK. And that basically takes you from, here's the wizard, let's generate some code. Now, what are we going to have to add in there in order to create our final product? And so these are some of the things we're doing to, that we hope will allow you guys to enter into Phoenix a little bit easier and have your students start using Phoenix at the beginning of the semester and work all the way through without too many hiccups.
So we have a few more minutes, and we've got some people who have real experience using Phoenix who were kind enough to come here and talk, as well as we've a number of members of the Phoenix development team here. So if there are any questions that you'd like to ask about Phoenix or using Phoenix, we'd welcome those questions. And I have a microphone here. Yeah.
So I wonder if each of the presenters would say what the best thing they found about Phoenix currently is and the thing they think needs the most improvement.
Okay. As long as you're here first.
Actually, the work we did, it was fairly straightforward to use Phoenix for. I mean, actually, that's the first thing you would try to instrument a program when you're learning Phoenix. So it was fairly easy to use. And the payoff was that in our current infrastructure, we couldn't get all the statistics that we wanted, which we were able to get through this system. So in that sense, we ended up with a more truer implementation and a true evaluation of what we did. As far as weaknesses are concerned, I mean, I think it's more of doing more complex things and learning about them. And for example, you know, we don't fully understand how to do the alias analysis within it. There's a lot of information in it, but we don't necessarily understand how to use it.
So for me, it was the system is very much like the systems that we were building for the whole National Compiler Infrastructure project. There's a lot of similarities in the goals, a lot of similarities in the organization. So that made it very easy for us to feel confident that the things that we want to do in the future were going to be able to be done and so forth. In terms of difficulties, I mean, last year I talked about how hard it was, and John has demonstrated here that some of the changes that they've made just to get started in the system. And to reiterate what Rajiv was saying here, there's still a lot of information that is hard to get at. Like, for example, with the register allocation work we were doing, you know, what really is the contract for the register allocation pass? What am I supposed to assume is true on the way in? What am I supposed to make sure is true on the way out? And just being able to uncover that kind of information is a little difficult today.
As for me, the main advantage of the current version of Phoenix is that we actually can work with .NET assemblies right now. In the previous versions, actually, so to say, we could not do that. It is a great advantage. And so we are using Phoenix IR. It's a very comfortable internal representation. As a very experienced expert in compilers, I should say that conceptually, a lot of ideas of Phoenix develop some earlier works. For example, there is a very famous book on compilers by Steve Machnik, and ideas of IR representation by triples and so on. I am quite familiar with it and with Steve Machnik in person. So I do appreciate that in Phoenix is a real commercial tool, or will be a real commercial tool in which these great ideas are implemented in such a full stream. And as for shortages, there still are some bugs. And we report them. Hopefully they will be fixed. And I have also one question to the Phoenix team. We are very interested in announcing Phoenix grants. Yeah, hopefully you will do that in future. Thank you.
So I'm actually an intern. I just came on board back in May, and I'm leaving in a few weeks. So I didn't really have that much time to catch up. But I was surprised at how little code it takes to start doing stuff in Phoenix. And how much is abstracted away, how much of a lot of the nitty-gritty details is abstracted away from the user. The add-in doesn't care whether a binary is managed or it's unmanaged. It opens it all the same and provides basically the same information. So a lot of that interface simplicity is really, really nice, and the ability to do stuff in only a few lines of code. As far as things that are needing improvement, this is ongoing, but discoverability of features and figuring out the heuristics or the behavior of certain kinds of certain systems, and figuring out what they are supposed to be doing and what they are actually doing is kind of difficult, but we're working on that, so that stuff will get better.
I don't have too much more to add. I'd say the barrier to entry was much nicer than a lot of the Java virtual machines that I've used. There's Java virtual machines that I would never give an undergraduate or even some of our master's students, and I easily give this tool, and I have, and the learning curve is so much smaller and manageable. And I say that the negatives, the one thing I'm disappointed about is I really love dynamic optimization, and the intent in the very beginning was to have plugins for the dynamic compiler, and because it's unmanaged, that's not going to be available. And so I was a little disappointed with that.
Okay, as a binary instrumentation tool, the API and interface is very straightforward, very similar to existing prior techniques, like on Atom on the Alpha. So that was a very easy thing to get going with. In terms of just things that need to be fixed, there's just a few interface issues for the binary instrumentation, such as instrument exit and a few just minor things, but I'm sure those will be worked out in the near future.
Well, that's really pretty much the end of time. So I want to thank you all for coming, and